Okay, so today we are discussing mechanisms and the steady state approximation. And so we'll go with our simple mechanism that we've already discussed, and that is the simple first order decomposition of A to some intermediate I, which occurs at first order rate constant Ki, and then that intermediate decays into the final stable product at first order decay Kp. And if we impose, of course, then that this is the slow step and this is the fast step, then we would recognize that our observed overall reaction rate would be Ki times A, and of course that would be negative as viewed for A. Okay, but suppose that we wanted to analyze this mechanism completely. If we wanted to put all of the differential rate laws together, we could do that. And what we would have to do is come up with an expression for dA by dt, di by dt, and dp by dt. So if we did that, we can write those out as dA dt is going to be negative Ki times A, and that's the only appearance where we see A. And recall, we've solved this before, and we recognize this gives us our first order decay in A, which would go as A at any time t equals A initial times exponential of negative KIT. Okay. We now put together the rate expression for the intermediate, di by dt, and we recognize this will be now here positive Ki times the concentration of A. Remember, it's always rate constant times reactants. And then now I appears in this second reaction, so we could now write this as minus Kp times I. And we would not get a simple, straightforward solution to this differential equation. So this is where we're going to eventually here take advantage of what we call the steady state approximation. And now, but we could solve this, though. This is not so complicated. If we did have more steps, however, we would certainly have to rely on the steady state approximation to solve this. And you'll see what that is momentarily. And if we came up with an expression for dp by dt, we recognize that will be the simple first order evolution of p, which will go as kp times I. Okay, and so now we know that we could solve this system of equations with Mathematica or some other program quite simply, but let's put this together and do it by hand so we can begin to appreciate what needs to be done. Okay, so I'm going to rewrite di by dt by putting in this expression for A. So we recognize that we can put this expression in here. Okay, and let's write that up here in the top corner. We'll write that as di by dt, and all of that is going to equal Ki times A initial times this exponential to the negative Ki times t. Okay, and then that will all be minus Kp times I. And now I'm going to rearrange this algebraically, and you'll see why in a moment. So if I now write this as di by dt, and I'm going to switch things around here and write that as plus Kp times I, and of course that all equals Ki times A initial times e to the negative Kit. Okay, so I put it in this form because as it turns out, this equation is a first order differential equation with a standard solution. That is dx by dt plus a times x equals b e to the negative c x. Well, this all, like I said, has a standard solution. And so we can apply that standard solution to my kinetic expression right here, and I'm just going to write that down directly. Okay, so I'll write that down here. So solution to the diffie gives us an expression for just the concentration of I at any time t. And that's a rather complex expression, but we'll write it all out. It's Ki divided by Kp minus Ki, all times, okay, e exponential raised to the negative Kit minus another exponential expression to the minus Kp t, and then that's all bracket, all times the A initial concentration. So we skipped a few steps in solving this expression, but again, this is because it had a standard solution for this first order differential equation. Okay, and then so now what we want to be able to do is come up with an expression for P at any time t. And of course, we have an expression already for A at any time t. And to get that expression for the concentration of product at any time, we recognize in my mechanism, I could set this up such that the initial P concentration is equal to 0, so I only have A. And with that in mind, then, the concentration of A at any time plus the concentration of intermediate at any time, plus the concentration of product at any time, which this is the expression, of course, that we want, equals the initial A concentration. So that is to say, we put some amount in A, and we allow this mechanism to proceed. And so, of course, then, at any time, my concentrations must add up to the original concentration of A that I had. And just using this simple algebraic expression, I can now solve an expression P of t, which is just going to equal the A initial, and then, of course, minus A at time t, minus I at time t. And then now what we have to do is rather cumbersome, but we can do it. It's no big deal. We can, of course, take this expression and plug it into right here. We can take this expression and then plug it into right here. And then, of course, A initial should just be a constant, and we can collect like terms. So we'll do some of the algebra here, and I'll pause for a moment, and you should pause the video, and see if you can come up with an expression simplified to best terms for P of t, and try to collect terms and eliminate as many variables as possible. So go ahead and pause it, and then I will put the solution up. Okay, did you pause it? Did you work it out? Hopefully you did. Here's the expression for P as a function of t, and that all distills down to the quantity 1 plus, and then this gets a little large, but it ends up being Ki exponential raised to the negative Ki times t, and then minus Kp all to the exponential raised to the K minus Ki times t. And then, let's see, that's all divided by Kp minus Ki. And And let's see, in parentheses and bracket, and then that's all times the A initial concentration. Okay, so that is our expression for P. We'll write down our expression for the concentration of I at any time T here, which recall went as Ki divided by Kp minus Ki, all times E raised to the minus KIT minus E raised to the minus KPT. And let's see, that's end bracket, and then that's all times the initial A concentration as well. So you can see really what these expressions are doing are either scaling up the A concentration, right? 1 plus these ratios of rate constants times A initial, or really it's scaling, as we'll see, first up and then down the concentration of I by the A initial concentration. Okay? And if we want to know where I maxes out, then of course what we really need is to know dI by dt, and I'll write all of that out. Okay, so we had a simplified expression for that, which recall was just based on our mechanism, but now with all of these equations in mind, I'm just going to plug all that in and write down the solution for you directly. So that it goes as minus Ki times A initial times Ki e to the negative Kit, and then minus Kp e to the minus Kpt. Okay, so end bracket there. And then all of that is divided by Kp minus Ki. And now again, if we wish to see where the intermediate maxes out, then we have an expression for the first derivative of I. And now we know that if we set that equal to 0 and solve for where t satisfies this equation, then we know we'll see the maximum where the intermediate is at a maximum. Okay, and if we examine this a little bit further, we might see that's a pretty easy way to make this all equal to 0. And that can just be accomplished by saying when this chunk of the equation all equals 0, so that's when Ki e to the minus Ki times t equals Kp e to the minus Kp times t, then of course this will equal 0, which will in turn make the whole expression equal to 0. And then now if we continue along and do some algebra on this equation, we rearrange and we get Ki divided by Kp, because recall, our goal is to solve for t. We're looking for t max, okay, for I. So rearranging this algebraically, Ki divided by Kp equals, then that's going to be the exponential of negative Kp divided by, exponential of negative Kp times t divided by the exponential of negative Ki times t. And if we do some algebra on this thing, we find that all equals, I'm going to write the exponential notation to make this a little bit easier to write. So that's e raised to the power t factored out times a quantity k minus kp, okay? And then now what I can do here is take the natural log of both sides. So I get natural log of ki over kp, and then this just ends up equaling t times ki minus kp. And then now finally, if I go and arrange this for t, let's put that up here, we would find then that t max equals 1 over ki minus kp times the natural log of ki over kp. And what's interesting about this expression is it will always result in a positive number. For example, if ki is less than kp, this expression is negative, But if ki is less than kp over here, the natural log of a number less than 1 is also negative, so negative negative gives you a positive. And then, of course, if ki is greater than kp, this is positive, and then this will be positive. So just a reality check that we did the correct algebra. Our time should be a positive quantity. And then now, if we were to plot this all out, if we were to plot out all of our concentration profiles, okay, and I'll put this on a relative scale, 1.0, where this could be, let's erase this arrow here. So if I put this on a relative scale, where again, in the concentration of any species J at time t divided by its initial value, where of course then at time equals 0, and at this y scale of 1.0, that's just the beginning of our reaction. And so we recognize, again, let's just write that mechanism down, right? A goes to I at first order decay, Ki, and I goes to product at first order decay, Kp. So we'd recognize A just shows a simple decay. Okay, so that is the concentration of A at any time. As we might guess, then our product shows a first order appearance. Okay, so that's this expression right here, concentration of product at any time. And so the 1 plus all these exponential functions are what give us this exponential growth. Okay, so that's P of t. And now our intermediate, it's hard to see how this equation, here it is, it's hard to see how that'll look. But if we were to plug in this expression for time into these expressions, then we would actually find that I first maxes out when when P and A are roughly the same, and then begins to decay. And as we'll see soon here, this is a case in which both Ki and Kp are very similar to each other. And we noted from this maximum time that it doesn't have to follow that the first step is the slow step. This second step could, in fact, be the slow step, and we would still see an expression that looks rather similar. The only limit is to observe this concentration profile where I is maxing out at roughly where A and P are equal. Then we note that Ki and Kp are similar in magnitude. But we'll see another case comes, and that's what we call the steady-state approximation, when actually Kp is much, much faster than Ki, and that's what we'll do next. Okay, so to summarize, when these two rate constants are very similar, we observe this reaction profile where I is rather dynamic. It's maxing out and then decaying. So let's look at a case in which these two rate constants are very different from each other. And that is what we call the steady-state approximation. Okay. Okay, so back to our simple mechanism where we get some decay of A and some evolution of P. And if we write this mechanism down again, all the same rate constants, all the same rate orders, all first order decay. But now, in the event where Kp is much, much greater than Ki, so in other words, where this reaction is very fast and this is very slow, then I doesn't really have an opportunity to max out. In other words, as soon as it's produced, it's going to be consumed. And what that does is it makes the production of I roughly equal to 0. In other words, di dt will be approximately equal to 0, And our reaction profile will look something like this for I. It will maybe have the appearance of maxing out, but generally it will remain fairly steady in concentration. So this is my concentration of I. Okay? So that is what we call a steady state approximation. And as you'll see, it makes solving these equations rather simple, or more simple, if you will. Sometimes they can still be a little complicated. So again, if we write out an expression for the rate of I, di dt, and that's equal to ki times a positive ki times a, right? Because I is appearing as a product. And then now minus kp times I. If we apply the steady state approximation, then we set this roughly equal to 0. And then now solving for I becomes rather straightforward. And I can just say now that the concentration of I equals, and I'm going to do a few of the algebraic steps. So I'm going to add this expression over, and then I'm going to divide out by Kp. Okay, and I recognize then my concentration of I at any time just equals Ki divided by Kp times A at any time t. And when I also go to solve for my expression dP by dt, which is just equal to positive Kp times I now have a simple expression in I that I can plug in right here. Okay, so we can take this and now plug it into I. And so if I go to do that, I can write dP by dt. And again, this is approximate because we made that steady state approximation. And that's going to be equal to Kp times Ki over Kp times AT. Well, and again, that just is all going to be equal to Ki times A of T, which is kind of cool because it's not what you would at first come up with. If you were writing dP dt from first principles, you would write it as positive Kp times I. However, because you've applied the steady state approximation, in addition to the fact that this step is slow, then of course the rate of appearance of product is just going to be given by the rate law of the slow step, which is exactly what we would have expected. So that's pretty cool. So if we continue along now and we want to come up with an expression for P at any time t, okay, I can integrate this side of the equation from 0 to t, and I can integrate, this side of the equation from 0 to t. And so because, of course, the concentration of product is 0 when t is equal to 0, this just becomes P of t roughly equal to, and then now I'm also going to recognize that I have an expression for A of t that was the exponential of negative KIT, so that just comes from the first order solution to A. And so then that's going to be equal to, KI. I'm going to pull everything out that's a constant, which is KI and A initial. And then now that's times the integral from 0 to t of E negative KI t dt. And again, this just came from the fact that A of t equals A0 e to the negative KIT, right? And so now I only have to integrate that expression. And when I do that, I get P of t equals, and then apply a little bit of algebra, A initial times 1 minus E to the minus KIT. So you should do this algebra on your own. Pause the video if you need to and see what you come up with. And this is actually really cool because this expression also will give us an exponential growth in P. Because remember, this is e to the negative KIT, so this expression will be negative. However, we'll have a positive number. It'll be negative, negative to give us a positive. And so that will give us an exponential growth. Okay, so I'm going to give you guys an activity here. So I'm going to erase everything, and I'm going to have you look at a real mechanism, and then I'll pause the video, or you should pause the video rather, so that you can apply the steady state approximation and see what kind of stuff you come up with. Okay, so here is a three-step mechanism. So this is the stratospheric decomposition of ozone. This is the simplified version of it, so we're not looking at it the catalytic decomposition, so we'll just look at it in simple terms. And the first step goes ozone goes through unimolecular or first order decomposition into O2 and single oxygen atom, and that happens at first order rate constant K1, and I'll just write unimolecular, in other words first order, right, unimolecular decomposition. The second step happens in which an oxygen atom reacts with an O2 to become an O3, and we'll call that K2, and for now we'll just chalk that up as a bimolecular second order reaction. In actuality, this reaction is a termolecular. It involves a third body, but to keep this simple for now, let's not worry about that. There's also another pathway that the oxygen atom can do. It can react with an ozone, and that can create two oxygen atoms. And that happens at rate constant K3, and for now we'll also call that the biomolecular decomposition. And if we were to then balance this out, and then considering the branching ratios, our overall reaction would be 2 ozones decompose into 3 O2s. And so a goal of this is to be able to come up with an expression, DO3 dt, so we know how much ozone decomposition is happening in the ozone layer. But we want to really come up with this expression in terms of things that we can measure, which is really going to be the concentration of O2 and the concentration of O3. It's rather difficult to come up and measure the concentration of a single oxygen atom, and you can apply the steady state approximation to do that. And so I'll give you the answer for it now. If we apply steady state and solve this mechanism, we could come up with a simple expression for DO3 dt, which goes as negative K1 times K3 times O3 squared, all divided by K2 times O2 plus K3 times O3. And again, this is a simple expression because everything involved in here, concentration of ozone and concentration of O2, we can measure these quantities. We've eliminated concentration of oxygen atom. Okay, so pause it. See if you can apply the steady state approximation and come up with this expression. Go for it. Okay, hopefully you did it and you got to it. If not, let's do it. So the way this goes is we write an expression for oxygen atom, and I'm going to get rid of this so that we have some more room here. Okay, so we'll write dO by dt, and that is going to equal positive K1 times O3, and then now we have to find all the other reactions where oxygen atom is a player. And so we can see it's in reaction 2 right here, and it's a reactant, so it's going to have a negative rate, negative K2 times O times O2, and it is also appearing as a reactant in the third reaction, so that's going to be minus K3 times O times O3. And if we apply the steady state, because hopefully what you came up with is that the oxygen atom is the intermediate, right? It appears and then it disappears. You apply the steady state approximation to the intermediate, which is the oxygen atom in this reaction. Okay, so now this would be a rather complex thing to solve. However, if we set the steady state approximation to 0, then we can come up with an expression for the oxygen atom concentration, which will go as this with some algebra involved here. K1 times O3 divided by K2 times O2 plus K3 times O3. Okay, so again, just from doing some algebra. And now, of course, I need to write the expression for ozone DO3 dt, and let's all write that down. So that's going to be, we go through the mechanisms, right? So ozone's a reactant in the first reaction, so that's going to be minus K1 times O3. And then now it appears as a product in the second reaction, so that's going to be plus K2 times O times O2. And then now it is a reactant in the third reaction, so that's going to be minus K3 times oxygen atom times O3. Okay, and so now we don't apply steady state approximation to ozone because it's not an intermediate, right? We have to solve this thing. However, because we have an expression for the oxygen atom here, we can plug this in to wherever we see that expression in the equation, which would be there as well as there. Furthermore, you might be thinking to yourself, well, I need to write an expression for DO2 dt, but actually you don't, because if you substitute these two in, then you'll eliminate all appearances of where concentration of oxygen atom appears. And so let's write that out. It'll be kind of cumbersome, but we can do it. So DO3 dt equals, and so I'm just going to keep this together as one big chunk here. So that's going to go as the following: negative K1 times K2 times O3 times O2. I might have to erase, yep, I'm going to have to make some room here. Okay, so hopefully you wrote all this stuff down. I'm going to get rid of it so I have some room to write it all out because it's a rather long line. So DO3 dt, so that's minus K1 times K2 times O3 times O2 minus K1 times K3 times O3 all squared plus K1 times K2 times O3 times O2, and then finally minus K1 times K3 times O3 squared, and this is all divided by K2 times O2 plus K3 times O3. So I skipped a few steps there in the algebra. Pause the video if you have to and see if you can come up with this expression from collecting like terms and getting a common denominator. And what you might notice from here, we can make a few simplifications. For example, these two terms are equal and opposite. So I can get rid of these. And let's see, is there anything else that I can get rid of? I think that I made a mistake in my notes. Okay, so let's see. I think I might have written down something twice. Yes, I think that I did not need this extra step, so I should have paused the video and made sure that I had done everything correctly, because then when we do that, we come up with the answer that I gave you, which was minus K1 times K3 times O3 squared, all divided by K2 times O2 plus K3 times O3. That's a 2 down there. Okay, and so this makes sense because we know that overall this should be a loss of ozone because the global reaction goes 2 ozones to 3 O2s, and we can see there is a negative sign right there in the rate. So, and if we were to apply all of our unit analysis, then we would also find that the units would work out. Okay, so that concludes your lecture on mechanisms and the steady state approximation. Thanks for watching.